All right, everyone, welcome. Thank you for joining this session on data analysis for renewable energy production. This session is part of Bellevue College's Earth Week, where we're exploring topics around the theme of climate voices, sharing, listening, and taking action together, which centers the importance of conversation, storytelling, and the sharing of knowledge as a powerful tool to spark action and build hope for a sustainable and just future. So my name is Alyssa Gordon. I am from the BC Office of Sustainability. We've got a really great lineup of events happening this week. So I encourage everyone to take a look at the full schedule, which I posted in the chat. There's still events happening tomorrow. A lot are on campus. And then Friday, we'll have more events as well. So I encourage everyone to check that out. And before we get started, I just wanted to go over a few details on Zoom etiquette, which I know we're all pros at this point, but just a few little things to go over. You're all muted upon joining the session. So I just ask that you continue to stay muted throughout the presentation unless you're prompted by the speaker or myself. Feel free to keep your camera on, as it does make for a more of engaging session for everyone, but that's totally your choice, whatever you're comfortable with. As a note, this session is being recorded to post on the sustainability website as a resource for the future. Throughout the session, please feel free to put any comments or questions in the chat box. Remember to be kind and treat everyone with respect there. We'll have a Q&A session at the end where you can unmute yourself if prompted or put your question in the chat box to be read. Feel free to message me if you're having any technical difficulties during the session, and I'll try to assist you as best I can. Lastly, I'd like to pause to acknowledge that Bellevue College resides on the traditional and occupied land of the Coast Salish peoples, past, present, and future. That includes but is not limited to Snoqualmie, Suquamish, Duwamish, Nisqually, Tulalip, and Muckleshoot. We honor their connection to the region, pay respect to the Coast Salish elders, past and present, and stand in solidarity through their struggles with continued systemic oppression. We commit to care for the land and water and center equity at the core of our learning. All right, so now let me take a moment to introduce our speaker today, who is a BC faculty member, Ted Spence. So Ted is a veteran of 3 decades of software engineering through a variety of industries. He has led projects at large companies such as Facebook, Knowledge Adventure, Vivendi Universal, and AST Computer, and helped to develop startups such as Lockstep, Avalara, and EEDAR. He currently teaches data analysis techniques at Bellevue College and writes for tedspence.com. He lives in West Seattle with his wife and daughter and has been known to bike down to Alki whenever the weather permits, which hopefully soon that will be often.
I'm really happy about that. Today's been a great day for it.
I know, it's been so nice. So everyone, welcome Ted. Thank you.
Thank you so much for that introduction. And one of the things that I'd like to say here is that we have an incredible opportunity to talk about something that is meaningful, exciting, and also very optimistic today. And that's really what got me excited to do this work on data analysis in the renewable energy market. So let me just start off with a question. And this is something that has been asked for decades at this point. Can we get renewable energy that is cheaper than fossil fuels? This is a really interesting question. And it's for a long time been one that people have asked, hopefully, without any real data behind it. So we would all prefer to have clean, healthy environments, and we would prefer to have our energy generated in a way that does not diminish or pollute our land. But let's take a look. Can we actually use the practice of data analytics to answer this question? So what are we going to do? We're going to look at this question and say, all right, we know that energy has a critical role in our day-to-day lives. And we know that electricity is an incredible core aspect of what it means to be a person in today's day and age. We all have electrical gadgets and electronic devices, we have computers, we have the internet, and all of these things are necessary. Well, how do we get that energy? What do we do? How do we use it? What are the factors that control whether electricity is being generated from one source or another source? how do we decide which techniques we're going to use to build our power infrastructure? And then finally, we're going to look at how does this turn into costs? Because everything that we do every day is a choice of how we are going to deploy our funds, how we are going to deploy our resources, our tax dollars, or maybe our public electricity market dollars. So everything that we do related to this can be tracked and it can be measured. And what I'd like to talk to you about is that the practice of data analytics can help us make these decisions. So very specifically, we're going to use data analysis to define these problems. We're going to say, what do we know about each type of energy generation? How do we know it? And what use can we make of it? And we're going to look at the ways in which we present these charts and look at this information in order to figure out how we can make our answers easier to agree upon. Because we all know that if you look at a gigantic spreadsheet full of data, or if you look at page after page of printouts of numbers, that's one way of consuming information, but good, well-designed charts can present information very effectively, and it can teach us a lot about how we view things. So a lot of my data analytics classes talk about how do we construct these charts and how do we turn them into something that can usefully answer a question. So let's jump in and let's go through a little bit of this together. I'd like to start with an overview of just electricity generation. And I'm going to focus, in this case, specifically on the United States. There are equally good charts, equally good data sources covering international data generation for all countries around the world, at least those countries that participate in this sort of data collection. We all know that there are some countries that don't really participate in international cooperation, but from the countries that do participate, we have lots of good information. In this case, we have a lot of good data for the United States. So let's start by asking ourselves, what's actually going on? How are we generating electricity? What does it look like? And I'm going to show you the first chart, and I think this is a nice colorful one. But this chart basically demonstrates how we are generating electricity over time. So for the moment, I'm just going to walk you through the elements of this chart, and I'm going to show you why I think this chart is a useful way to talk about the challenges that we're facing. So obviously we have here colors, and these colors are pretty easy to break down. You've got this color over here, which is brown for coal. You've got this color up here, which is blue for natural gas. You've got this red bar in the middle, which is for nuclear energy, and a green bar for renewables. And there's this very small sliver on the top, which is really interesting. It's for petroleum products. And I didn't really know this going into this research. There are actually a couple of places throughout the United States where we as a country make use of petroleum and petroleum products to generate electricity directly. Now, this is actually something that is relatively rare nowadays. If you can see this chart, at one point it was very common. If you see about halfway through the chart, at one point this data was very common, but it's kind of slimmed down to nearly nothing. So let's go ahead and let's add back in some of the metrics and axes for this chart and use it to tell us something about this data. First thing we're going to look at is 1955. This point in the past was 1955. And in 1955, there was virtually a tenth of the electricity that we use today. So in that era, we were making very little use of electricity. And I think there's some obvious causes to this. Obvious causes being that we didn't have as many home appliances. There was a time when people were gradually beginning to add refrigerators to their homes. People were gradually beginning to add dishwashers and other electric appliances. And these things gradually started increasing the day-to-day electricity use of our household. And as we can see, this was a very steady incline. So from the period of 1955 up until about 1973, you can see very steady growth, whereupon something interesting happens. in about the early 1970s, you see that there was a lot of electricity use, or sorry, a lot of electricity generation that was coming out of petroleum. And we can imagine, looking at this, that there was probably a reason why petroleum energy generation stopped being used here, because you may remember from your history books that there was an amazing OPEC crisis that happened in the 1970s, and they started increasing the cost of petroleum and petroleum products. So you can imagine that there was a period of time when petroleum products were used in a very expensive fashion, but it's gradually kind of faded out after the oil shocks of the 1970s ended. You can also see that at the beginning of the 1970s, we started to make use of nuclear power. Now, this is actually quite interesting to me. I had somehow thought, before going into this, that electricity generation from nuclear power was common in the 50s and 60s. As it turns out, it was not. As it turns out, in the 50s and 60s, virtually the only usage of nuclear power was governmental and military in order to produce materials for nuclear weapons. So it was only about the early 1970s when we as a country started making use of nuclear power. And the next key thing that happens is around about the year 2000, we actually see electricity usage peaking. And somewhere between 2000 and about the year 2005, we essentially stopped using more electricity. Now, I have more electric devices today than I did in the year 2000. I have more internet routers and Wi-Fi devices and everything. But what's also happened is regulations have stepped in to ask the creators of these devices to increase their efficiency. So starting around the early years of the 21st century, we see electricity demand peaking. And as a result of that, we are not constantly building new power plants the way we used to. On the other hand, what you see is that the power mixture is changing. So let's break this down a little bit farther. Starting in the 1990s, we began to see modern fracking generate a lot more natural gas. It took quite a long time. It took quite a long time after we began using modern fracking to see the effects of that change, because sometime around 10 years after fracking became common, that's when the cost of natural gas started to plummet. Interestingly enough, renewable energy has been growing relatively steadily since 1992. It started in 1992 at about 327 billion kilowatt hours, and it's roughly a little bit more than doubled to 792 billion kilowatt hours today. Strangely enough, nuclear power is really unchanged since 2004. So for about the past 15 years, nuclear power has not changed. We're going to get into that a little bit in a few minutes. And obviously, you can see that the experiments with petroleum have kind of faded. And I want to point out to you that I'm including on these slides here all of these links to the sources for all of these various facts and charts. We'll publish this online later, and you can always click through it if you like. So if you stop and you say, let's set aside the history, let's just look at what we're doing today. What we can see today is that we've actually got three almost equivalent generation sources: renewable energy, nuclear, and coal. These three sources each form about 20% of our electricity generation needs. Then we have a gigantic chunk. Natural gas forms about 40% of our electricity generation. There's a reason for that, and we'll cover that in a second. But it's also worth saying that energy generation is all over the map, quite literally, and also in a pun form. So this chart here shows the electricity generation for all of the different states in the United States. And I know that this chart is a little bit too small for you to see all of the details, but what you can take out of this is that every state in the United States has a very different approach to generating electricity. So countries and states and jurisdictions and all sorts of legal reasons people have historical attachments to methods of generating electricity. The state of Tennessee is home to the Oak Ridge Nuclear Research Facility, was one of the first sites of any nuclear power generation in the United States. It is still primarily a nuclear power state today. West Virginia, on the other hand, is very famous as a source of coal. And as a result, you'll find that West Virginia is still very heavily focused on coal generation today. So there are other decisions besides cost that influence how we generate electricity. And you'll probably know that the state of Washington, where we live, is almost entirely hydroelectric. And part of that is because it just rains a lot here. It rains a lot here, and as a result, we have lots of rivers. And because we have lots of rivers, it is relatively straightforward to put a dam on a river and capture hydroelectric power. And it's relatively cost effective. And as a result, our cost is about, our electricity mix is about 2/3 hydroelectric. We also do make use of natural gas, nuclear, and other places, but we don't have any significant renewable energy using solar photovoltaic. People do have solar panels on their rooftops, but this chart measures utility scale generation, so we don't see it here. All right, so that's a look at the overall United States. Let's dig in and let's look at each individual method of power generation. Let's see what data can tell us about each type of power generator. So the first thing we're going to look at is coal power. And as we saw from our chart, we are seeing less and less coal power used today. And that trend started about 15 years ago, and it's been kind of accelerating recently. So what is going on? Well, the first thing is coal power generation is incredibly simple. As we know, coal power generation is one of the very first types of electricity generation that we discovered in the industrial age of humanity. It's because all we do is we heat things up, and coal is very good at heating things up. It's really easy to dig coal out of the ground and burn it. So a coal power generation plant is essentially a burner, and you light a whole bunch of coal on fire, and it heats up water, and that water turns into steam. Steam turns the turbine, and then the water condenses back out of steam again and goes back through a second time. So the only real change that has happened to coal power generation in the past 100 years is that we have started to add scrubbers to our coal power plant. You'll see it's kind of like right about here in the chart. There's a set of vertical lines, and those are essentially supposed to be scrubbers that take some of the pollution and remove it from the smoke that the coal power plant generates. Well, an interesting thing is that because coal power plants have been around for an incredibly long time, there is also a huge amount of variability in the cost effectiveness of coal power plants. This chart right here is called a distribution chart, and this is a cost distribution chart. What it tells you is here are all of the different power plants in the United States, and here is for each power plant the cost level that it produces electricity. So what you can see is that there's a handful of extremely cost-effective power plants. All the way at the far end of the chart, colored in green lines, those power plants generate energy very cost-effectively. But on the other hand, at the extreme end, you have electricity generation that is almost 10 times more expensive. So a big part of the reason that coal power plants are changing their usage is because gradually power companies are shutting down the inefficient, cost-ineffective coal power plants. And there's another challenge here, which is that if you take a power plant that's not earning a lot of money and you turn it off for a period of time, turning it back on again costs more money. So what you have is a situation where the least effective coal power plants in the United States are gradually becoming less and less and less cost effective, and they're gradually being turned off and replaced with alternatives. And this is probably a good thing because there's another really big important bit to talk about coal power plants, which is coal ash. This right here, and I'm just going to step out of frame for a second. This right here is an image of coal ash pollution that emerges outside of a coal generating power plant. And what you can see is that this makes different parts of our environment very unpleasant, and it kind of renders us poor stewards of the environment. We have to spend lots of money to clean it up. In many cases, the companies who make this pollution will go bankrupt after paying everyone lots of bonuses and allow the government to use tax dollars to clean it up instead. So what you can see is that this is really something that is a risk, and people are eliminating this risk by gradually phasing out these coal power plants. Unfortunately, there is not enough research into coal power plants to be able to say definitively how much this harms human health. There have been a number of studies, and there have been a lot of different researchers that have invested time and energy into this, but data analysis is very poor at directing, at detecting actual causation from something that happens indirectly, like this type of pollution. So the research that exists out there can tell us that there is a correlation between living near a coal power plant and respiratory disease, lung cancer, cardiovascular disease. We can tell that there's a correlation, but data analysis is not going to give us a conclusive bit of proof. We know, for example, that these things are happening, but we cannot definitively state that coal power is the cause of it. So at the moment, all of our data and all of our research suggests that these things are linked, but we as data analysts have to be careful and precise when we speak about these things. We know that there are scientific reasons to believe that this is happening, but we also have to be as honest as possible with our data. And right now, our data tells us that we recommend that these power plants be closed wherever possible, but we cannot conclusively state the cost of this. So regardless of whether or not we are able to give very specific prescriptions for how to view the health data, whether or not we are able to do that, we can very clearly state that natural gas is cheap. It produces less carbon dioxide emission per electricity generated. And it has an interesting benefit, which is that natural gas is dispatchable. And we'll talk more about what dispatchable means in a minute. So as we have gradually replaced some of our coal power plants with natural gas, our carbon dioxide emissions have dropped significantly. And if we continue to retire coal power plants, we can expect that our carbon dioxide emissions will wind up at a fraction of their peak from about 2005, was about the time when we had peak carbon dioxide emissions in the United States. So this is something that's very hopeful. And if you ever look at the fate of environmentalism in our country, we have a lot of doomsaying and we have a lot of warnings, but at the same time, there is a lot to be excited about. And this chart right here shows me one of the reasons that I believe we should be excited about the work that's going into renewable energy today. I'd like to talk a little bit now about hydroelectric and geothermal power, because in contrast to coal, hydroelectric power and geothermal power is extremely popular. And it's not only popular, but it's something that we all like and enjoy every day. And I happen to be able to say that I have personally experienced a lot of these power plants, and the experiences have been a lot better than coal ash. So the first one that I'd like to point out is one of our favorite places out here, Snoqualmie. We obviously have a very large power generation plant at Snoqualmie Falls. It generates a significant amount of electricity for the Seattle area, and the wastewater that is produced by this plant is still pure water. It is still pure, clean water, and I've gone out on an inner tube on the warm days of the summer, and I've floated around enjoyably on this river, and you can see that this type of power generation is incredibly cost-effective and incredibly good for our environment. The challenge, though, is that some places where power generation has happened, we have also wound up using dams. And dams have other effects on the river. Perhaps you've seen the Coleman locks where we have the salmon ladder. It takes cost and energy and research to figure out ways to help the natural wildlife to cope with the building of dams and locks. But end result is that hydroelectric power is incredibly successful, and we should be very lucky that all of our, or a significant portion of our electricity in Seattle comes from it. Something else that is incredibly popular is geothermal energy. And this is a picture of a really fantastic place in Iceland called the Blue Lagoon Resort and Spa. The Blue Lagoon Resort and Spa is in fact the wastewater dump for a geothermal power plant. It is the Svartsengi geothermal power plant. When they installed this geothermal power plant, they figured once the water has been used to turn the turbines, we will just dump it out on the ground, and it'll soak back into the ground and the plants will drink it up. Well, as it turned out, the water had a little bit of clay in it, and that clay formed bowls, and it wound up being rather nice, enjoyable little pools. And the people of Reykjavik would come out there and visit and take a swim in the pools. And after they did that for a little while, they said, wow, this is really popular. Let's turn it into a resort. So I've actually gone there and I've enjoyed it, and it's really fantastic. And so this is an example of how we can generate power without destroying our environment. In this case, literally transforming a section of volcanic turf into a lovely collection of pools that people can enjoy. So if hydroelectric and geothermal power are this good, you may ask, why don't we use more of it? Well, the answer is that there are some significant limitations to hydroelectric power generation. There are some significant limitations to geothermal power generation, and it's basically that you can only build this in locations where the geography of that, the geology of that area permits you to. So climate change equally well is limiting the number of places where we can build dams. This screenshot here, these photographs here are from a relatively recent disaster. The Oroville Dam in California was a very significant source of power generation, and it was also affected by some intermittent droughts and intermittent rainstorms that overwhelmed the power generation. So eventually they had to open their spillways, and the volume of water rushing over the spillways was so significant that it tore up the spillway. And as a result, they had to spend years repairing it. And I think it's finally gone back into service now. But all told, we make as much use of hydroelectric power and geothermal power as we are able to as a country. Unfortunately, that also means that there are not a lot of other power sources for hydroelectric and geothermal available to us. The estimates today is that there's only about 65 gigawatts of hydropower available if we tapped everything. And you know what? Every year we're adding about 42 gigawatts of wind power. So I think at this point we've already done as much as we can as a country using water-based power. Well, the next thing to ask is, if we are in need of electricity, can we make use of nuclear power? And I'd like to talk you through some very interesting challenges, because nuclear energy, of course, doesn't generate coal ash. It doesn't like spew out polluted water the same way that a coal power plant does. It doesn't generate acid rain the way a coal power plant does. But on the other hand, nuclear power has something that is probably even more significant. It has a public relations problem. And this public relations problem happens because nuclear power plant incidents are incredibly large and visible. And when they happen, it is national, worldwide news. If a coal power plant breaks down, it often doesn't even get into the news, because in general, a coal power plant can only affect a small area of the country. And as a result, things that go wrong with it are often buried. We as a society, we focus on big news about huge things that rarely happen, rather than the small incremental disaster that happens on a day-to-day basis of pollution of our waters and our grounds. So this is a screenshot from a famous TV series from about a year or so ago called Chernobyl. And it's a fantastic TV series, and there's a lot of really good science in it. But what it also shows is that people are not really comfortable with nuclear power. So let's try to quantify that. As data analysts, rather than saying, hey, people don't like it, we need data. So let's gather some data. This data shows public sentiment on nuclear power. And what you'll see here is that in this chart, nuclear power is continuing to waffle back and forth between eras when it is in favor due to public support and eras when it is out of favor due to a highly publicized incident. And what you'll see here is that the Fukushima incident, I think, happened in 2011, if I can remember correctly. But the Fukushima Daiichi nuclear power plant issue kind of set people into general state of concern, and the overall optimism that people had in the early 2000s for nuclear power has diminished. But you know what? This is still 50-50. We have a situation where at least half of our country strongly or somewhat favors nuclear power. So why aren't we building new nuclear power? Why are we still at the exact same stage for nuclear power that we were at 15 years ago, 20 years ago? Well, there's a different answer for that. The different answer is that nuclear power building has stopped for two key reasons. The first reason is that no nuclear power permits have been issued since 1979. When 3 Mile Island happened in 1979, we as a country stopped issuing permits for nuclear power plants. So this red line on the chart shows the number of permits that have been issued for nuclear power plants. And what you can see is that there's actually a huge gap between the blue line being the number of power plants that exist, number of nuclear power plants that exist, and the red line, which is the number of power plants that are permitted. So why are we not building these power plants that are permitted? The answer is that at the moment, it takes between $5 to $12 billion to build a nuclear power plant. $5 to $12 billion, and it takes from 5 to 10 years to build a nuclear power plant before it becomes operational. So remember back to my earlier slide, our electricity usage as a country is no longer growing. Because our electricity usage is no longer growing, there isn't a huge need to rapidly build incredibly expensive power plants. We kind of missed our window. We were building them relatively quickly way back when, and there just isn't the ability to build them anymore because there is no longer a demand for a chunk more electricity. These massive costs and lead times make it hard. Oh, darn it. 1 second.
You're on mute, Ted, or we can't hear you.
Testing my audio again? Okay.
Oh, there you go.
Yes, unfortunately, I have this fantastic headset, which is wireless, and it ran out of batteries. So let's continue on. Okay, so the next issue that happens with nuclear power is that the uncertainty is a problem. This is a photograph of a nuclear power plant called the San Onofre nuclear power plant. It's famous. It was in movies like Naked Gun. It has a very interesting and unique shape. But at the same time, this nuclear power plant was happily generating electricity for many years, and then it was very briefly taken offline for some regular maintenance. And when it was taken offline for maintenance, the people doing the maintenance work discovered that there were faulty tubes that were leaking steam. So they decided to extend the maintenance and figure out what to do about these faulty tubes. it took them a year and a half to figure out what they wanted to do with those tubes, because the tubes were part of the core power generating utility. And it was going to take a lot of work to figure out what to do and how to safely do it and how to change it. Well, after about a year and a half of study, the company that owned this power plant, Southern California Edison, decided that they did not want to spend money keeping this power plant in a state of semi-readiness. So they said, look, it just doesn't make sense. We don't know what it's going to take to fix this power plant. We are going to shut it down rather than try to fix it. So what you've got is you've got a situation where it will cost you $5 to $12 billion to build a plant. It's uncertain whether anyone needs it. And then it's also uncertain whether your power plant will stay intact and stay functional for long enough for you to get a profit off of it. This is why we're not building nuclear power today. Next thing we're going to look at is natural gas. Natural gas is super popular. And the reason why it's popular is because it has become cheap. And it also does not generate the same kind of massive coal ash pollution that we saw earlier. So natural gas electricity has dropped in cost by about a factor, well, to about a third of what it used to cost a couple of years ago. You can see by this chart that we used to be up around 12 cents per kilowatt hour, and now we're down to about 4.5 cents per kilowatt hour in fuel costs. And this is basically because fracking has made natural gas incredibly cheap and affordable to retrieve. Now, another interesting thing is that natural gas is dispatchable. A natural gas power plant you can turn on and off, just like your stove. And as a result of that, natural gas power plants are incredibly useful for electricity. I see some questions, and by the way, I will actually give you a chart at the very end that details exactly what they all cost. So please hang on for that, and you'll get to see that in a minute. But another thing that's interesting is even though natural gas costs are coming down, residential electricity costs are not declining. So we'll have to figure that out. Dispatchable power is preferred because we look at day-to-day usage in electricity as a thing called a demand curve. When we are asleep, the electricity usage and the electricity demands of our country are relatively low. When we wake up, there's a little bit of electricity demands. When we go to work, there's a little bit of electricity demands. When we turn on our air conditioning in the heat of the day, there's an increased electricity demand. And then in the evening, when we turn on our TVs and our lights to watch TV and read books, we have increased electricity demand. Well, something that's really useful is that natural gas power plants can be turned on and off in about a 10-minute period. A hydroelectric power plant is even faster than that. It can be turned on or off in about 10 seconds. If we actually plugged in a grid battery, we could turn on and off the batteries in milliseconds, but that's often not needed. And compared to this, our coal power plants take hours to heat up and cool down. So this is a big part of the reason why coal power plants are dropping. You can see this chart here. It shows how each power plant is configured so that it can be turned on or off as needed. This is often the point where people ask me questions about batteries. And the question is typically that we hear about things like Tesla batteries or these utility scale batteries that are being plugged in Australia. Well, these things are really amazing, but they are also very expensive at the moment. So the challenge is that if we take standalone, here we are, standalone solar photovoltaic, and then we add batteries to it, it increases in costs by a pretty significant amount, somewhere around doubling to about somewhere between 50% increase and doubling in cost. As a result, batteries are just not yet ready. They're not yet cost effective for our industry to put in place. On the other hand, there is something incredibly cost effective that we can look at, which is a fantastic technology called wind power. And I want to start off by showing you, this is actually something that I used to drive through. When we would go out into the mountains as a young child, I used to drive through this pass. And in the early 1980s, they started installing these wind turbines. And the early wind turbines were experiments, and they were tiny little things, and they would spin sometimes, and then they would break down, and sometimes they would catch on fire. But you know what? The people that were doing this, the San Gorgonio wind farm, they kept coming back year after year, experimenting with new wind turbine designs. And because they kept experimenting year in and year out, they got better and better and better. And eventually they made a lot of progress. This power plant generated 615 megawatt. Oh, darn it. I can't remember whether this is megawatt hours or megawatt like consistent generation. I'll have to find that out. But one of the really interesting changes that has happened is the size of these wind turbines continues to increase. And they have gotten to the point where we are looking at 500-foot tall wind turbines that are being installed offshore right now. These wind turbines are amazing in size, and this size allows the turbines to capture more of the wind, and not only to capture more of the wind, but to capture more reliable wind. The way wind works in our atmosphere is that the areas that are higher up tend to have more consistent, steady winds. The areas that are low down tend to have relatively still air that sometimes gusts a little bit. So these rapid increases have dramatically shifted our cost generation. We have this entire section of the United States, kind of down the central path of the United States, that just has very steady, consistent high winds. And these very steady, consistent high winds are perfect for wind generation. And as a result, people continue to build larger and larger turbines in these central states, and more of our electricity can be generated from wind turbines. What you'll find is that Texas is actually one of the states that has an incredible amount of renewable energy usage, which may be something that surprises you due to the reputation that certain states have for attitudes towards renewable energy, but it's incredibly cost effective, and it makes very successful electric generation in this particular area. Another thing worth saying is that countries like Ireland, Ireland is not likely to ever have a lot of solar photovoltaic power generation. Well, they can make use of wind power, and they can do a great job with it. This is a chart from an Irish Twitter account that shows how much of Ireland's power is generated from wind turbines. And what you can see is that for the entire month of February, over 50% of Ireland's electricity was generated from wind power. Let's also talk a little bit about solar photovoltaic, because this is pretty amazing here. And the key thing that I want to get at is solar panels are absolutely astonishing. Solar panels were introduced in 1954. They were used in satellites. And gradually, people discovered that the technology that builds our televisions, our LCD televisions, is also applicable to building solar power plants. Televisions are one of the things that continue to decline in cost amazingly. So how are solar photovoltaic cells changing in cost? This is one of the most amazing charts. This is actually called a logarithmic distribution or an exponential distribution. What you can see is that the cost of solar photovoltaic modules has declined at an exponential rate over the past 40 years. And these cost declines are really staggering, and they've made a huge difference in what used to be a very expensive way to generate power. It's now become one of the cheapest. If you can see right here, way off in the chart, this is when Jimmy Carter put solar panels on the White House roof. And I think maybe he was actually looking pretty far ahead. I think that was a pretty interesting visionary moment in history. So that exponential chart is less useful than this one right here. This is a logarithmic chart. And what you can see from this logarithmic chart is that there's actually a pretty much straight line. This straight line goes almost directly down. And you can predict the cost, right here. You can predict that the cost of these solar power plants is going to continue to decline because we continue to see these same reductions in cost year over year, regardless of where we are at. What are these actual cost reductions? Well, about half of the cost reduction in solar power plants is due to the module cost. We also have soft costs, installation costs, inverters, and a whole bunch of things. But the key realization here is there's a thing called a learning rate. And a learning rate is what we call the Henry Ford Model T effect. When you start doing something over and over and over again, when you start building something with mass production, when you start installing lots of solar photovoltaic panels, you get lots of practice doing it. And so over time, we find that the learning rate of solar photovoltaic electricity is 39% year over year. That means next year, we expect solar photovoltaic electricity will be 39% cheaper than this year. And it just keeps going, just keeps going. An interesting side effect of this is that solar power has generation peaks. Solar power is incredibly effective from about 12 p.m. to 3 p.m. And that basically corresponds to when the sun comes out every day. So in theory, we can generate a humongous amount of solar energy during these actual peak daytime periods. And what it's doing is it's allowing us to shut off other more polluting versions of power during the time when solar energy is very active. So again, let's go back to the solar photovoltaic battery question. Can we put batteries on solar photovoltaic panels? Well, let's look at the learning rate. We're making incredible progress in the cost reductions of batteries, but unfortunately, batteries are just not getting cheaper fast enough. The learning rate for batteries is only about 13% per year. So that means that at the current rate of growth, batteries are not going to catch up with solar photovoltaic. And we just don't see this being an immediate likely change in our electricity generation habits. So having said all of that, we're getting close to the end of this presentation. Let's take what we've learned and put it into a little bit of math. We've learned that coal power plants are out of favor, cost of fuel, cost of cleanups, dispatchability. Nuclear power plants are out of favor due to highly publicly visible incidents. Natural gas power plants are cheap, cost-effective, and dispatchable, which makes them incredibly appealing. You can also transport natural gas from one place to another. Hydroelectric and geothermal plants, we have about as many of them as we could ever have. And we're not likely to invent new rivers, so it's unlikely that this is ever going to change. Wind power and solar photovoltaic have made incredible progress, and they can be implemented in places where we have a deserted stretch of land or basically anywhere we have access to sun. Well, I won't bore you with this. This is the slide I had to put in there because out of all of these lessons, we've actually figured out there is this thing called levelized cost of electricity. And whenever people say, oh, but what about this? But what about that? Well, the answer is levelized cost of electricity is the total amount of electricity generated by a power plant over its entire lifetime divided by its total cost over its lifetime. And what that means is that every factor that is involved in building it, staffing it, cleaning it up after it gets shut down, all of those costs are factored into this. Even such things as insurance, lending costs to borrow money to build the power plant. So we have incredibly good and accurate numbers for how expensive these power plants are to build. And this chart shows what progress we have made with renewable energy over the past decade. In 2010, solar photovoltaic electricity was the most expensive way to generate electricity. Nobody was doing it. Today, solar photovoltaic energy has dropped down below the cost of the majority of fossil fuel power plants. Solar photovoltaic energy has become one of the most cost-effective ways to generate electricity. Onshore wind is gradually pulling away from the pack. This darkened area right here is what's called the cost range. It's the central percentiles of fossil fuel power plants. So the majority of fossil fuel power plants are in this slightly darkened bar. And what you can see is nowadays, it is cheaper to build an onshore wind power plant in most cases than it is to build a fossil fuel power plant. So this is the slide that I promised you earlier. These are what the actual costs are today. And what you can see is that it costs somewhere around $95 per megawatt hour to build a nuclear power plant. So obviously that's pretty high. People aren't going to do it. It costs about $40 per kilowatt hour in order to take an existing nuclear power plant, retest it, validate it, and extend its lifetime for a little bit. So you could see that it might be cost effective to extend the lifetime of some nuclear power plants. Coal is clearly not cost effective at this point. Natural gas is incredibly cheap, but on average, solar power is cheaper than natural gas. On average, wind power onshore is cheaper than virtually everything except natural gas. And these sources are either by the United States Energy Agency or by IRENA, the International Energy Agency. Where possible, I have used United States costs here. Something that I think is incredibly hopeful is we could retire all of our coal and all of our coal power plants with solar and wind, and we could actually save money at this point. So if we retired the remaining coal power plants in the United States, we could save about $5.6 billion per year. And so not only is this going to reduce coal power pollution, not only is it going to reduce carbon dioxide emissions, but it will also save us money. So I think this is one of the really incredibly optimistic things that renewable energy and data analytics has to teach us is it's not just something that improves our environment, it's also something that makes us as a country richer and more productive. If you look at this, this is a chart that shows how new capacity is coming into play. Every year, we are adding new renewable power that is cheaper than the cheapest fossil fuel fired options. This chart shows only those renewable power energy that's being installed worldwide that is cheaper than the cheapest available fossil fuel power generation. So there's incredible work that's happening, and it's very exciting to know that we as a society can gradually replace these polluting power sources with ones that have been proven to be cost-effective and renewable and non-polluting. Here's a great quote. I love this. Jimmy Carter said in 1979, when he announced the solar photovoltaic heater, sorry, I think it was just a solar heater, not a photovoltaic plant. He said, a generation from now, this solar heater can either be a curiosity or it can be a small part of one of the greatest and most exciting adventures ever. And what I can say is that today, a world record was set, $10 per megawatt hour in Saudi Arabia for a solar photovoltaic power plant. That's 4 times cheaper than the average natural gas-fired power plant. Wind power also reached an amazing milestone. Just recently, on March 29th, 2022, wind power briefly became the second largest source of electricity generation in the United States. And that was because wind power continues to be incredibly cheap. You don't have to staff a wind power plant. You don't have to hire someone to be on site with hard hats, checking out steam tubes or anything. You install it and then you walk away. And as a result, wind power is continuing to be built, and it's continuing to make a tremendous improvement in our country's cost effectiveness and the quality of our environment. So the conclusions after doing all of this research is that we have incredible opportunities. Solar and onshore wind power are the most cost-effective sources of electricity today. They cannot, unfortunately, replace everything. But if you were to combine them with natural gas, you could wind up with incredibly cost-effective, low carbon, low pollution electricity. And you can do it with technology that exists today. And you don't need to go out and invent something radical and new. You just have to install what we already know how to install today. And this is something that I think also shows the value of producing good charts and making use of data analysis to tell a story, because with this, I am much more confident in our future. So I just want to say thank you for coming and joining, and I'd like to open up some time for questions. Alyssa, would you be willing to moderate, please?
Yes, sure. So far, we just have that one about what the cost is, and I believe you covered that. I'm not sure if you touched on if there's any plans to start issuing new permits for building nuclear plants.
So the reason that that's probably not an issue is because if you wanted to build a nuclear power plant, you could simply pick up one of the existing permits that already has been issued. So if somebody did realistically want to spend $5 to $12 billion to build a nuclear power plant, there would be nothing stopping them from doing that. They could simply go to somebody who holds one of these existing permits and say, I would like to use this permit. I will build this power plant. I'll pay you a nominal sum because you are sitting on it and you aren't doing anything with it. So there's nothing stopping people from building nuclear power plants except for the fact that nuclear power is not cost effective. It just simply isn't. If you said, I want to build 100 megawatts of power generation, you'd probably be better off building a wind farm in Nebraska. And you'd make more money, you'd earn more profit, you'd have a smaller loan, and you could generate as much electricity as you wanted based upon how much space you could purchase.
Thank you. That's really informative.
No problem. I know there's always a lot of excitement about nuclear power because nuclear power seems very straightforward and reliable. And the challenge is that there's other things that impact it. And really, dispatchability continues to be the #1 determinant, that people are building dispatchable power so that they can turn it on and off when needed and save costs.
Solar is actually extremely promising based on all the information that you provided. What's the limiting factors for solar, aside from like the innate limiting factors like it's on during the day and off at night? What's stopping the US or what's stopping America from really implementing this at a mass scale? I guess it kind of is, but even more.
This demand issue, this is what's called capacity factor. So this chart right here shows how the capacity factor of solar energy affects California energy. So this chart is actually from the California Independent Systems Operator. And so what California did is they started building as much solar power as they could stand, because of course it's always sunny in Southern California, right? I know I live there, it's kind of depressing. I came here because I like seasons that change. Anyways, Southern California, you can get as much power out of solar as you want. The problem is that it's only during this peak time of the day. So in California, they could probably double their solar power generation, but it would only allow them to turn off other fossil fuels during the daytime. So until there is a way to increase dispatchability of solar power, you will probably see limits on solar power installations. So solar power will most likely get to the point where it could nearly cover all of the electricity needs of the region during the day. But once it gets to that point, there's no advantage to building more of it. And you still have to have things like natural gas and wind available for the other areas. I think it's always going to be part of the mix. And I wish I could say that batteries were going to do it. I think what we're going to see is solar power plants built where it's sunny, wind power plants built where it's windy, and power is going to move from one part of the country to the other. We're going to see needs to build more transmission lines from places where electricity is cost effective to places where it is needed.
Thank you. That's really informative. Well,
you're welcome. If anyone has other questions, please feel free to put them in chat. Otherwise, I'd like to say you've been a fantastic audience, and thank you so much for giving the opportunity to dig in and research something that I think is a very encouraging and optimistic take on the future. I think sometimes when we look at the modern world out there, sometimes we only look at the things that are going badly. And this, to me, is an opportunity to look at the amazing progress that has been made over the past decade and how we have cause for enthusiasm and encouragement, excitement about the possibilities of the future.
Is there any possibility we could have access to this PowerPoint?
Certainly, I would be happy to share it. Alyssa, can we publish this on the Earth Week site after this is done?
Sure. Yep. I can make it available on the sustainability website.
Of course, we will publish that, and we will, I'll put it out on my Twitter account as well.
Awesome. Well, great. If there's no more questions, I just want to thank Ted for this great informative session today. It was really eye-opening and relieving, like you were saying, just to see how the data shows, the cost shakeout in favor of renewable energy. So I hope everyone learned something new, and we'll use that new knowledge to engage in meaningful conversations with your friends, families, colleagues, and neighbors. Thanks everyone for coming. We hope to see you at more Earth Week events. Most of the events are in person tomorrow, which is really exciting. We have an activist who works on protecting forests in the Pacific Northwest. We have a Repair What You Wear workshop where you can come in and learn how to fix the holes in your jeans, attach new buttons to keep your clothes out of the landfill. So I highly encourage everyone to check out the schedule. And other than that, I hope everybody has a great rest of your evening.
Thank you so much, everyone. It's been a pleasure, and good luck to you all.
Thanks again, Ted. Thanks, everyone.